Hey there, discrete math friends. I hope all is well. I'm excited to meet you again on Tuesday via Zoom, but I thought I'd give you a little bit of instruction first. We're going to be talking about 3 different sections this week, and one will be the binomial theorem. Then we'll talk about mathematical expectation, and finally we'll run into conditional probability and Bayes' rule. So a fun week, an interesting week. It always reminds me of my grandfather. He's passed on, I don't know, 5, 6 years ago, but he was a math and physics teacher for 41 years. And so he wasn't real touchy-feely. He wouldn't go up to your granddad and get a hug and kind words, or it wasn't mean ever. He was very nice, but he was always just interested in doing problems. And so when I would go over to his house, he would give me math lessons. And I'll just give you one little math lesson that you may have heard before. One day I was sitting in his living room on his couch, and he said, "Do you know that I can read your mind?" Well, you may have seen this trick before, but I'll see if it works for you. So as you're listening to this video, I just want you to pick a number between 1 and 10. Just pick a number, put it into your head, or write it down if you want to. Pick a number between 1 and 10. Now I want you to take that number and multiply it by 9. So you picked a number between 1 and 10, you multiplied it by 9. Now I want you to take the number that you have, and if it's a 2-digit number, I want you to add the digits together. And then I want you to subtract 5. Now you have a number, and I want you to pick the letter of the alphabet associated with that number. So A is 1, B is 2, C is 3, and so forth. So at this point, you have a letter. If you don't, you can go back, rewind a little bit, and repeat the process. I want you to take that letter and think of a country in the world that begins with that letter. Think of a country in the world that begins with that letter. And then I want you to think of the second letter in that country. Then I want you to think of an animal that starts with the second letter in that country. And I want you to think of the color of that animal. Now, if you're a little bit lost, you can pause right now, go all the way back, and repeat it. You should be thinking of an animal and a color. And this doesn't work for everybody, but a lot of people are thinking of a gray elephant. So if you're thinking of a gray elephant, I was when I was a kid. I remember sitting there just in awe. I thought, my granddad is a wizard. My granddad is amazing. He can do anything. And the reason I bring that up is that we're going to be talking about the binomial theorem. And the binomial theorem, it starts out with or is related to Pascal's triangle. If you've not seen Pascal's triangle, I'm going to show you Pascal's triangle. I got to get my whiteboard situated as well as possible. So Pascal's triangle looks something like this. I go over to my granddad's house, and he's writing this pattern. And I'm thinking, this is maddening because it must be easy. And I'm coming up with ideas for what comes next. And I'm usually wrong. And then he'll just write the next row. And the next row, and the next row. And at some point, either you figure it out or you've seen it before. But yeah, all I'm doing is I'm taking the 2 numbers above the number in between, and I'm adding them together. 4 plus 6 is 10. 6 plus 4 is 10. Pascal's triangle has all sorts of really cool patterns within it and applications. And we're going to just look at a couple of them. The one that we're going to be really interested in is its relationship between our combination counting function. So you might remember this formula from last week. If we want to count combinations of size r taken from n objects, and another way to write that, like a different notation for it, would just be n with r in parentheses around that. So what did we do? We took n factorial over n minus r factorial times r factorial. That was a formula from last week. And what's really interesting, if you look at Pascal's triangle, 1 is actually 0, choose 0, 0, C0. This is easier to write in here in the midst of the triangle. And then this right here, this one right here is 1, choose 0. And this is 1, choose 1. This right here, this one is 2, choose 0. And this is 2, choose 1. And this is 2, choose 2. And again, when I say choose, I'm talking about the combination counting function. Well, you might be seeing this pattern, and you can check it if you want to. You could do 2, choose 1 is 2 factorial divided by 1 factorial times 2 minus 1 factorial, but you'd get 2. This right here is 3, choose 0. 3 combinations of size 1 is 3. 3 combinations of size 2 is also 3. And 3 combinations of size 3 is 1. So we actually can kind of create another look to Pascal's triangle, or the combination counting function that generates these same values. This would be 4, choose 0, 4, choose 1, 4, choose 2, 4, choose 3. It's not divided by. And 4C4. So it just so happens that these numbers in Pascal's triangle are generated by the combination counting function, which leads to what's called Pascal's formula. And this is in our book. Pascal's formula basically generalizes that the two things that happen above a particular thing, a general thing, can be added together to get the next thing. So Pascal's formula looks like this. N plus 1, choose R, equals N, choose R minus 1, plus N, choose R. It's just a relationship between combinations, and it comes from, well, it comes from the triangle and observing the fact that you can add these two combination counting features to create this combination counting feature. But you can also prove it real easily using this definition for N choose R and algebraically walking through the fact that this must turn into this or vice versa. And if you want to, on Tuesday, we can actually prove that together in the Zoom session. It might be in the exercises. I can't remember if I assigned it or not. It'd be a fun little test question. It's not terribly tedious, but I'll spare you for the moment. So at this point, I just want you to remember the combination counting function. I want you to notice Pascal's triangle and how it's constructed, and that it's also constructed by sums of particular counting functions turning into kind of a next counting function. So that's really, really significant and interesting, and has lots and lots of uses. Well, now what I'm going to do is something that seems totally different. It seems unrelated, and yet it's completely related. So keep this in mind. And I'm going to take you back to something that you used to do in Algebra 2, probably loved it, called binomial expansion. So a binomial is just two things. And a generic two things would be A and B. So A plus B will be our generic binomial, and expansion means to take that to a power. So A plus B, I'm going to start with to the 0th power, but anything to the 0th power is just 1, right? So no matter what A and B are, if it's to the 0th power, we get 1. Now I'm going to expand a plus b to the first. Well, a plus b to the first is just a plus b. A plus b to the second is actually, remember, that's a plus b times a plus b. So if you FOIL this out, you get a squared plus an ab plus another ab, that's plus 2ab plus b squared. So you FOIL this out and you end up with a squared plus 2ab plus b squared. A plus b to the third, we're just expanding the binomial by the next power, and that actually would be a plus b times another a plus b, or a plus b squared, which we just found out was a squared plus 2ab plus b squared times another a plus b. So this actually gets really tedious, and the algebra gets traumatic, maybe. Once you do this and simplify, you end up getting a to the third plus 3a squared b plus 3a b squared plus b cubed. At some point you decide, I don't want to keep doing this, but not yet. So a plus b to the fourth. Maybe you decide, I don't want to keep doing it this way. I don't want to keep doing algebra because it's just long, it's tedious, it's not that interesting, but I think I'm finding a pattern. So if we were going to expand a plus b to the fourth, which is a plus b times a plus b times a plus b times a plus b, what would we get? Well, it looks like if you walk through the previous expansions, the first thing ought to be a to the fourth, and it is. And let's see, what's the next thing? The next thing is, well, it's actually 4a to the third b, plus the next thing turns out to be 6a to the second b to the second. The next thing turns out to be 4a b to the third, and as might be expected, the next one is that is given to us. So let's see what a plus b to the fifth is. Well, as expected, you can see the pattern here. It's going to be a to the fifth, and that power ends up showing up as the next coefficient. The coefficient is the number in front of a term, so it actually is going to be 5, and then, yep, you're seeing it. It's a to the, you can see the powers on the a go down by 1 each time we move to the next term, and the powers on the b, this is b to the 0, b to the first, b to the second, b to the third, b to the fourth, so this is going to be b to the first, plus, but the next coefficient is actually a little bit tricky to figure out. Like, what goes here? I'm pretty sure it's going to be a to the third, b to the, see, am I running out of my room a little bit? Trying to keep these aligned well enough. So this is plus something, a to the third, b to the second. What's that something? Well, it's actually 10. What's the next thing going to be? It's going to be a number. It's going to be 10. A to the second, b to the third, plus 5. We do have symmetry. 5, a to the first, b to the fourth, plus b to the fifth. So what I'm hoping you're noticing is we do have a pattern here. The pattern is that it always starts with a, the first thing, to the expansion power, and then the power on a drops by 1 until we have the last term is a to the 0. And as a mirror, we have b to the 0, b to the first, b to the second, b to the third, b to the fourth, b to the fifth. But sometimes that coefficient, the number in front, is a little bit tricky to figure out. You can kind of see that it's a 1 in all these cases, and that it's a 1 in all these cases. But maybe you notice that whatever power is here shows up right here as a number. And then these get trickier, the 10 and the 10. But if you remember Pascal's triangle, you can see this 5 actually comes from the 1a to the fourth plus 4 of these. So the coefficients above match. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1b fourth is 5. So there's that. There's a couple of other ways to notice this pattern too. If you number the terms, like this is the first term, this is the second term, the third term, the fourth term, the fifth term, and the sixth term. And by the way, there's always one more term than the expansion power. So let's see, how would we get the 10? Well, here's one way of getting the 10. If you take the coefficient, this 5, times the power on a, that 4, 5 times 4 is 20, divided by the term number is 2, turns into 10. 10 times the power on the a, 10 times 3 is 30, divided by the term number is 3, 30 divided by 3 is 10. 10 times the power on a is 2, 10 times 2 is 20, divided by the term number 4 is 5. So one of the ways that we can see a pattern going across the row is coefficient times power on a divided by term number equals next coefficient. So there's sort of a recursive element to figuring out the numbers that go in front of the letters. And then finally, and this is actually leading to the binomial theorem, because we noticed earlier that there was a pattern of NCRs, a pattern of combination counting functions within Pascal's triangle, you can actually figure out that this 10 right here is 10 by doing 5 factorial over 3 factorial times 2 factorial. This 10 right here, you can get that by doing 5 factorial divided by 2 factorial times 3 factorial. In fact, you can get any coefficient you want in a binomial expansion by taking the factorial of the expansion power, that's why we have a 5 here, divided by the factorials on the a term and the b term. And that's called the binomial theorem. I'll write it out for you. I'm going to erase this, so if you want to pause it or take a picture or whatever you can. I'm going to erase this, but the binomial formula is going to help us expand binomials that they add degrees of complexity to, and it's going to actually help us calculate what are called binomial probabilities. So I'm going to erase this. And the binomial formula or theorem is written as a sum, at least it is in our book. So it says a plus b to the sum, we'll say k going from 0 up to n of n choose k. This is the combination counting feature, and you can write NCR if you want to, because it means the same thing, times a to the n minus k times b to the k. So a problem that you might get, I think there's one like this in the homework, is it'll say expand x minus 4y to the fourth. So let's say you have x minus 4y, but it's to the fourth. And what you need to do to start with is you need to remember that the a represents the first thing. So a is really just x in this problem. And b is the second thing. Notice I have a minus here. So b needs to end up being negative 4y. So you could write like plus and then put a negative 4y in parentheses. Whenever they give you a problem and a or b or both is something more complex than just one letter, you want to put it in parentheses so that when you expand it out, you don't lose things like negative signs. So let's just write this out. And if you want to, you can follow through with this formula. But to me, I can kind of remember what we were just doing. And it might just be more easy to memorize the process than the letters in the formula. So you'll see how they connect, though. So what happens is the first thing in this expansion is really just a to the expansion power. So the first thing is x to the fourth plus the next thing we remember maybe from Pascal's triangle is always the coefficient is whatever power is here comes next. So 4, and then it's a, the first thing, which happens to be x to 1 power less, and then it's b to the first power. Well, b is actually negative 4y. And don't simplify yet. Let's just leave it in sort of a plus b form. Plus, well, what was that next thing? Well, if I can't remember, this binomial formula tells me the next thing is actually going to be the factorial of the expansion power divided by the powers on the a and the b. But we know that the a, which is really x in this problem, is going to be to the second. And we know that the b is now also going to be to the second. By the way, the powers on a and b, if you add them together, always equal the expansion power. So this coefficient out here is actually going to be divided by 2 factorial times 2 factorial. Let's see what comes next. Well, it's almost easier to get the a and the b and their powers before you get the coefficient. So the next thing is going to be x to the power on x is going down 1. So it was x to the second. Now it's x to the first. And the power on the b, the minus 4y, is going up. So it's to the third, which means that the coefficient, the number out front, is actually the expansion power factorial over, this is x to the first. So you can write 1 factorial if you want to, times 3 factorial. We're almost there. Plus, well, x has just gone from x to the fourth, x to the third, x to the second, x to the first. Now it's x to the 0. We're at the last thing, which is really just the b, the negative 4y, to that expansion power. At which point you'll want to do some simplification, and I don't know that I want to do all of it here on this video. It's just taking a while. We're already at 22 minutes, but remember, when you have a string of things, you can revise it a little bit. Like this is 4 times x cubed times minus 4 times y, but the minus 4 times 4 can turn into negative 16 x cubed y. 2 factorial is just 2 times 2 factorial is 2. 2 times 2 is 4, but we've got a 4 factorial on top, which is 4 times 3 times 2 times 1. But remember, this right here is 4, and so you could cancel out that with the 4 on top, and 3 times 2 is 6. So this would be plus, but let's be sure of looking at all the simplifications that can happen. So this is going to be 6, but then there's a times, and that's actually not times negative 4 because that needs to be squared. So negative 4 squared is actually positive 16 times 6. So whatever that is, 16 times 5, I guess, is 80, plus another 16, is that 96? 96. And then we've got an x squared, and the y also needs to be squared. So make sure that you're simplifying things okay. There was still an x to the fourth at the beginning. Might as well finish this off. 4 factorial, 4 times 3 times 2 times 1. But 3 factorial is 3 times 2 times 1. So those cancel out. Oh boy, this is going to be fun. We've got a minus 4 cubed. Minus 4 times minus 4 is 16 times minus 4 is negative 64. But then we have times another 4. Negative 64 times 4, 60 times 4 is what, 240 plus, oh man, you do it. So we've got negative 64 times 4, x to the first, y to the third, and then plus negative 4 to the fourth. It's going to be positive 16 times 16. Oh, is that 256? 256 y to the fourth. So a little bit tedious, but this is equal to this in green, this expanded version of that. So fun problems like that. Theoretical problems where there are a lot of algebra to do. And then sometimes you get these probability questions that you might not think make use of this, but I'll show you why. So let me do one more. And we'll call this binomial probabilities. Our book doesn't have a whole lot of these problems in it, but they're interesting and they show up every once in a while in our book. But if you take an engineering statistics class or regular statistics class, you'll get lots and lots of these. So let's just do an example. Let's say I'm going to shoot 10 free throws. And the probability of making a free throw is 70%. So I'm shooting a free throw. There's a 70% chance that I make it, a 30% chance that I miss it. And binomial probabilities have to have two outcomes. So if I shoot it, I either make it or I miss it. It's either a girl or a boy. It's a win or a lose, success or failure. And we're going to say find the probability of making maybe 8 out of 10. Probability of making 8 out of 10. Well, what I'm going to do is I'm just going to write out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces. And if you remember back from the first part of the chapter, the probability of something happening and then something else happening and then something else happening and then something else happening, as long as the events are independent and you don't change probabilities with each thing, which in this case, you know, if I missed a whole bunch of free throws, I might get mental. And my likelihood of making it might not be 0.7 because I'm thinking about how many I just missed. But for this problem, it is 0.7, and you do have independence, which is required for binomial probabilities. But in this case, I would say, well, the likelihood of making 8 out of 10, I've got 10 spaces. And suppose I said, well, the chance of making the first one is 70%. And means times, maybe I make the second one at 70% and 70%. If I'm talking about making 8 out of 10, there's actually going to be 8 of those positions are going to have a 70% chance of a make. And then 2 of the positions will be misses, so a 30% and a 30%. So it might seem like the probability of making 8 out of 10 would be 70% to the 8th times 30% to the 2nd. The problem is this scenario literally is showing a make on the first shot, a make on the second, a make on the third. The 4th is a miss, and the 7th is a miss, and the others are makes. Oops, I should have put another 0.7 there. In reality, we need to mix up the 0.7s and the 0.3s in such a way that we consider every different way in which we can miss 2 and make 8. And actually, this is really just the Mississippi problem again, because there are 10 characters that if you want to figure out how many ways to rearrange them, there would be 10 factorial ways to rearrange them. But look, it's like crazy Mississippi problem where there's 8 0.7s and there are 2 0.3s. Everyone got the Mississippi problem, the bookkeeper problem right on the exam. So essentially what you have to do for these binomial probability questions is you take the probability of a success to the power of the number of successes times the probability of a failure to the number of failures, but then you have this multiplier out front that is the two powers added together factorial divided by those individual factorials of the powers. And that actually perfectly matches terms in a binomial because you've got like an a to a power times a b to a power, but the powers together add up to the expansion power. And this really is just 10C8. So whatever this turns out to be, that's the likelihood of making 8 out of 10 free throws. And make sure that you view this video, try some of the questions on the homework, and then email me and tell me what you'd like to cover on Tuesday's class. I'll send another video on mathematical expectation, but hopefully you enjoyed this presentation on the binomial theorem. Take care. Have a great day. Bye-bye.